I have a program running on this microcontroller board, just a while loop running forever, and for a lot of embedded programs, that's all you need. But the more things you add to your program, the harder it becomes to keep everything running properly in a single superloop. And at some point it starts to make sense to use a real-time operating system, where you, instead of a single superloop, split your program into multiple tasks that can run independently. But at what point does that actually happen? Well, I've got a bunch of parts here, and in this video we're going to add them one by one to this board and also expand the code until we see that happen, to hopefully get a more practical understanding of what a real-time operating system actually gives us. We can begin by adding this potentiometer and servo motor, and simply make the motor follow as I turn the knob. To keep it smooth and responsive, we will need a fast update rate, something like 100 Hz, so that it doesn't feel laggy. Overall, fast update loops like this are common in embedded systems, so it's a good real-time example to use. The code needs to read the pot value and then translate that into a corresponding servo angle. But with this, we now get two things that needs to run at different rates. And we can't just put one delay after the other, because then their timing affects each other. But that's easy to fix. We can just use timestamps instead. And by the way, like a chef on a cooking show, I've already prepared the drivers so that we can just focus on what matters instead. Then compiling and flashing this. And there we go. The LED blinks as before, and the arrow follows smoothly when I turn the knob. Next, we can add this 16:2 LCD display to show the angle and the uptime. Same pattern as the others. A timestamp variable and an if statement, updated every 100 milliseconds so it's smooth and doesn't flicker too much. Yes, the display updates nicely and angle changes as I turn the knob. We now have three independent things running at different rates: the LED, the potentiometer and servo, and the display. Adding more is straightforward. We can just drop in another timestamp if block. At this point, this is no longer just a loop with some if statements. What we have here is already a system that's trying to schedule work, and it makes sense to think of these things as tasks now. We can even make that explicit in the code by creating a struct task storing the function to run and how often, and rewriting the main function to instead looping over these task functions. Adding a new task is now just a matter of adding a new line to this array. The code is functionally the same as before, but now it better matches how we naturally think about the system. One blinks the LED, one handles the motor, and one updates the display. Separate jobs, each minding their own business. And what we just built actually has a name. It's a cooperative scheduler. In its simplest form, each task runs, does its thing, and hands control back. We call it cooperative because each task has to cooperate and give the scheduler a chance to run the next task. But a cooperative scheduler has its limitations, and to understand that, we can look at what happens if we add a task that doesn't cooperate. Say for example we connect a slow communication interface, like a UART with low baud rate, and then create a task that sends a big chunk of data over it every few seconds. And because it takes some time to send this data, and our scheduler is cooperative, it means the other tasks will have to wait. And we can see the consequence of that when we now run this. When the message is transmitted, the LED blinks inconsistently, the display lags, and the motor stutters. We say that the UART task is blocking the other tasks, causing them to miss their deadlines. This is the limitation of cooperative scheduling. It only works when everyone cooperates. One straightforward way to fix this would of course be to just make the UART task cooperate so that it doesn't block the other tasks, and there are several ways you could do that. You could use interrupts and transmit the next byte on every TX interrupt until all bytes are transmitted. You could set up DMA and let that transmit the whole thing without involving the CPU. Or you could just break the transfer into smaller chunks and let the other tasks run in between. And sure, you could do that, but as the program grows, you end up having to do this for every task that causes problems. And soon your logic is split across interrupts, state, and timing checks, and you're no longer dealing with one task at a time, which kind of was the whole point in the first place. And eventually you get the program that is just one big mess. There must be a better way. What if instead of fixing each task one by one, we try to fix it in one place, in the scheduler itself? The problem right now is that the scheduler has its hands tied behind its back. It has to wait for each task to give control back before it can switch. And as we saw, that becomes a problem as soon as one task takes too long. So what we need is for the scheduler to have the ability to take control from the UART task, in our case, while it's running, pause it, and then switch to the other tasks that needs to run, and then come back to the UART task again. Fortunately, we have a mechanism for this, called interrupts, and they can stop what the CPU is currently doing immediately to run an interrupt function. So instead of running the scheduler from the main function, we can run it from an interrupt function and configure a hardware timer to fire it very often, for example every millisecond. In this new type of scheduling, we don't wait for the task to give control back like we did with the cooperative scheduler. Instead, the scheduler can preempt the running task and switch to something else, so we call this preemptive scheduling. But this type of scheduling does complicate the scheduling code, because when we interrupt a task like this, we can't just lose where it was. We need to pause it and later continue exactly where it left off. That means saving its execution state, registers, stack, yeah, everything. So that when we resume it, we can restore its state and it can continue like nothing happened. And yes, implementing this is absolutely possible, but it takes quite a bit of work and involves architecture-specific assembly code. And it would be a kind of unnecessary thing to do, because what we just described, a timer-driven preemptive scheduler, is exactly what sits at the core of a modern real-time operating system. So if you ever reach this point, the more reasonable thing to do is usually to just use something that's already built and battle-tested. And that's what I'm doing here. I'm implementing our tasks using a proper RTOS instead, each task running its own small loop. Look at this. Everything running smoothly. Motor follows the pot. Display updates. LED blinks. And we are transmitting over the slow UART without affecting anything else. So from the outside, it's working nicely. But to really see what the RTOS is doing for us, we should look at the execution timeline too. And we can do that in Segger System View, which is a trace tool that shows what the RTOS is doing over time. The slow UART transmission still takes about 500 milliseconds, but now only it is affected, and the other tasks still run when they are supposed to. The LED every half second, the display every 100 milliseconds, and the pot servo every 10 milliseconds. If we zoom in, we can see that the scheduler interrupt fires every millisecond, regardless of what any task is doing. That gives the scheduler a regular chance to check if something else should run, and if needed, it can switch to another task, even if the task that was running has not finished. As a result, one slow task doesn't lock up the whole system anymore, and time-critical tasks still get a chance to run when they need to. This is what a real-time operating system allows us to do. It allows us to design the system to meet timing requirements. And it's not just that it solves our immediate problem, it also gives us a different way to think about the program. Before, we had to constantly think about how long each part of the loop was allowed to run, because one part could block everything else. With a preemptive scheduler, that changes. Each task can be written more like its own little program. So instead of one big superloop, we now get something that feels more like several smaller loops running side by side, each thinking it has the whole CPU to itself. But while this is powerful and solves our timing problem, we now run into a new problem when we start sharing data or resources between tasks, because then they start interfering with each other. Let's look at an example of this. If we make each task regularly print something to the UART, we get a situation where multiple tasks are using the same resource, the UART peripheral. On their own, each task is still fine, but when we run this, the output is sometimes garbled, because several tasks are now trying to write to the UART and their writes can get interleaved. Coordination problems like this are common when working with multiple tasks, so alongside the scheduler, RTOS also gives you tools to coordinate access between tasks. One of those tools is a mutex, which lets us protect the shared resource so that only one task can use it at a time. If we run this again, the output now looks fine, because each task waits for the UART to be free before it logs its own message. With this approach though, each task still has to wait while the log message is transmitted, and that can still be a problem for time-critical tasks. In our case, for example, we don't really want the server task spending time on something less important like logging, so another common way to handle this is to introduce a dedicated logging task and have the other tasks send log messages to it through a queue. The log task that we get here now, one can say, is a bit different from the other tasks, because instead of running on a fixed schedule, it normally just blocks and waits. And when another task puts a message in the queue, this logging task wakes up, writes the message to the UART, and then goes back to sleep. And this is not just useful for logging, this is also a common way to handle asynchronous events overall. That's event-driven design. Tasks don't need to keep running just to check if something happened. They can sleep until there is actually something to do. But also, once tasks can block, wake up and wait for events, the scheduler needs a way to decide what should run first when multiple tasks are ready at the same time. And not all tasks are equally important. For example, the pot server task is more time critical than the display or logging. That's where the concept of priorities comes in, which lets us rank tasks according to their importance. Now with this, if multiple tasks are ready to run, the scheduler will prefer the higher priority pot server task and the display task. In practice, choosing priorities is usually more involved than this. There is also a cost to all of this RTOS machinery we've just talked about. The scheduler, the queues, the mutexes, the priorities, and so on. More flash, more RAM. This is a debug build, so the numbers are a bit inflated, but you get the idea. Each task has its own stack, so the more tasks you add, the more memory you're committing. A lot of it is configurable. Which features are enabled, priority level, stack sizes, heap sizes, and more. As you should realize by now, a real-time operating system doesn't remove all complexity. It comes with new problems you have to deal with. But at the same time, it gives you building blocks to help you deal with them. Building blocks that are standardized and well understood. Okay, so that was all I wanted to say in this video. And I hope that this has given you a practical introduction to what the real-time operating system gives you over using a simple superloop. The project I used here, I deliberately simplified that for the sake of the video, and to be honest, it would have been fine to just use a superloop here instead. But the point was more that once you start noticing the clues, when parts of your program takes a long time and you have something else that is more time critical that needs to run, or you are starting to think about things in your program as tasks, or simply spending more time on bookkeeping than on the actual problem, then it might be time to consider a real-time operating system. Here I used FreeRTOS, and I think that's a good place to start, because it lets you focus on the basic concepts of a real-time operating system without distracting you with things around it. In my professional work, I also like to use RTOS a lot these days. But that's more of an embedded ecosystem, so it can be a bit more confusing to start with. Regardless, I think it's more important to know when to consider an RTOS in the first place.